So, lesson 6, more friction. Nick, I'm going to pick on you. Nothing bad. Nick, have you ever pushed the benches in the gym across the floor by sliding them? So I'd like you to imagine, because example 1 says, consider the bench below, which is being pulled by student 1, that'll be you, across a rough surface, let's say the gym floor, which has some stickiness, at a constant speed. Oh, you know what? What 2 words should I underline if I'm a good physics student? Because that's probably going to be key to doing this question. Okay. Suddenly, student number 2, Cole, pushes down on the bench. He sits on it. Okay, can you all imagine? You've probably seen this happen, where someone's been pushing the bench and one of their friends has come along and, I'm going to sit on it. If you don't change how hard you push, if student number 1 maintains the same constant applied force, what happens to the A, weight of the bench, B, normal force of the bench, C, friction, and D, motion of the bench? You know what? Let's go A, B, C, and D. Can you use your imagination? You got what we're talking about here? Nick is pushing the bench along at a constant speed, minding his own business, and then big bad Cole comes along, sits on the bench. What's going to happen? What happens to the weight of the bench? Well, first of all, when I say weight, when I say weight, what am I really talking about? What's it a synonym for? This is important. You need to know this for the test. I think it's also sort of on your formula sheet, but it's worth having in your memory. Yeah. More specific. mg. Okay? So you can make a little note here. mg. Nick, when Cole sits on the bench, does the mass of the bench change? No. mg stays the same. So is the reason that things change because the bench changed? No. What happens to the normal force? You know what? This is a job for a free body diagram. Now, I did the free body diagram for the original situation right here. Now we have an extra push down. What are the forces acting on this bench? If we get the obvious one, there's still mg. Don't write this down, just look up, why must this be wrong? If I drew an arrow pointing up the same size as mg, why must that be impossible? Is this bench? Yeah, Mateo.
Because the weight of the bench and plus Cole's weight is hitting it.
Okay, right now, this is not balanced. Right now, I have an unbalanced force down. This would be sinking into the ground like quicksand. By the way, quicksand, the reason you sink in quicksand is the force down with gravity is larger than the normal force that it's capable of creating, so you will sink into the ground, into the quicksand. If you're ever on something that you sink into, it's because you're demanding more of its normal force that it can give out. But the ground is pretty stable. So the normal force would have to cancel out gravity and the extra push. It would be about that long. You okay with that? So B says, what happens to the normal force? Nick, what happened to the normal force when Cole's... That's the change in this situation. I don't want to write... Oh, you know what? How about this? Fn, arrow up. Increased. So what happens to the force of friction? How do you know? Friction is what times what? Say that again. Friction is what times what? And what force just got bigger? The normal force, so friction had to get bigger. Okay, that's what's going on there. So friction got bigger. So in my free body diagram, suddenly friction does that. Are my forces balanced anymore? Who's winning? In my picture, who's winning? Yeah, friction. Who's losing? Nick's applied force. So which way is this? Which way must this accelerate? Yes. Now it was moving forwards. It's accelerating backwards, so it's going to slow down. First it's going to slow down, okay? And then very rapidly, as it slows down, it's going to reach its minimum speed, which is 0. Now, as soon as that happens, friction then, don't write this down, becomes as, it just matches the applied, because if it didn't, it would suddenly start moving backwards, and I know it doesn't do that either. So there's really quick things going on here. Coal increases the normal force, which increases friction, which means you're going to decelerate, but as soon as you come to a stop, now friction is only as big as it needs to be, and it'll just match you. So if you want to, you can kind of say the second one will be matching the applied. You don't have to write that in if you don't want to. I just don't want you to think that suddenly it's going to start accelerating backwards and coal's going to get a free ride across the gym. It doesn't work that way. And we know that. So what's going to happen to the motion?
Slow down.
Slows, and then eventually stops. Okay? It says explain your answer using principles of physics. I think we really just did up here in our discussion. Is that all right? And what you notice this time is the normal force, once coal sat on the bench, was no longer equal to mg. That's what we're going to be talking about today. Situations where the normal force is more complicated. And this is why you've never heard me say friction is mu mg, even though it was in all of your lesson 5 homework. Friction is mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force if I'm clever with my free body diagram. I also need to point out something else. There's actually 2 different types of mu. 2 different types of friction. How many of you ever have just tried to slide something really heavy across the floor? Any of you? Okay. So try to remember it. You may have noticed, if it's really heavy, getting it moving is tough, but once you get it moving, you don't need to push as hard to keep it moving. You notice that? That's because technically there's 2 different types of stickiness, 2 different types of coefficient of friction. So I wrote down here, there can be friction on an object even when it's at rest because those microscopic hills and valleys, they settle into each other and they interlock. This force of friction on an object at rest is called static friction. Because static means not moving or changing. So, I'm going to stand up. I'll keep the recording running if you hear me talking on YouTube. Here's my desk. If I pull on this with exactly 2 newtons and the desk does not move, which of the following statements is true? Static friction is bigger than 2 newtons? B, static friction is exactly 2 newtons? Sorry, is exactly 2 newtons? C, static friction is less than 2 newtons? D, there is no static friction. You know what? Since there's choices, C, we get to vote. How high we hold our hand up is how sure we are of the answer. So up here, I'll pull on my desk. If I pull on my desk with exactly 2 newtons and it does not move, who says, A, Mr. Duke, static friction is clearly bigger than 2 newtons because it's not moving? A, 1, 2, 3, 4, 5. Okay. Who says, no, Mr. Duke, static friction is exactly 2 newtons? B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Is that a vote, Emma? Oh, okay. I think I said 17. Who says C? Who says D? Convince me. As always, you can attack or defend. You can say these answers must be wrong or my answer must be right. Are 5 of you right or are 5 of you wrong? Convince me. Why must D... Oh, yeah, go ahead. What are we defending or attacking?
I'm defending.
Convince me.
Since the desk is at rest, all forces must be down.
Yes. The desk is at rest, so the forces must be, I'm looking for a word that begins with the letter B, balanced. Must be. If they weren't, unlike what the Ministry of Education seems to think, if forces aren't balanced, it's going to be accelerating. But if they are balanced, you can't have a change in motion. So if it's at rest, it'll stay at rest. If it's in motion, it'll stay at a constant velocity in a straight line. So, B, what law did you use for that?
Oh, for
Okay, so you can write in your notes Newton's first because you came up with that, and if you knew that that one is called Newton's first, you can write that, or you can write if forces aren't balanced, it will accelerate, which is the description of Newton's first. I know Newton's laws, and I'm a nerd, so I'm going to write Newton's Newton's first. Okay. Why can't A be correct? Because if it was bigger, if I let go of the desk, it would have to go shooting that way like a slingshot or something. And watch, it doesn't. Static friction is only as big as it needs to be. Static friction is what prevents you from moving an object. The word static means at rest or not moving or unchanging. So what if I pulled with 5 newtons? How big is friction? If it's not moving, 5. What if I pull with 5.1 newtons? How big is friction? Now, suppose the biggest friction, static friction can be, is 15 newtons. If I pull with 14.9, it's still going to be 14.9 in the other direction. If I pull with 15, that's the feeling that you get when you can tell through your hands it's just about you're ready to move. Right there. Once it starts moving, you're going to find, however, that friction becomes smaller. So static friction acts when you have two objects at rest relative to one another. Static friction is what keeps a car parked on a hill. It's the friction between the tires and the road. A block of wood will remain stationary on a ramp until you increase the angle past a certain point. Then it'll start to slide, but static friction is what's keeping it from moving. Static friction is what you feel when you first throw your weight against an object to try and start it to slide. The force to overcome static friction is always bigger than the force needed to balance sliding friction. The fancy word for sliding friction is kinetic friction. And so if I'm going to be fussy, Maggie, for every situation there's actually two mu's. Mu static, and I put a little s, and mu kinetic. I use this one if we haven't started moving yet in my free body diagram. I use this one after we've started moving in my free body diagram. Which one's bigger? Mu static or mu kinetic? Which one's bigger? That's why it's tougher to get something moving in the first place. Why? You may have noticed this if you've ever been in a pickup truck on a bumpy gravel road. If you go really slow, the tire hits every single rut and divot. You can feel every bump in the road. But if you go medium fast, you actually skip over a lot of the potholes. Your truck shakes a little bit, but it's nowhere near as bad as if you go really slow. Static friction, those microscopic hills and valleys have had a chance to settle into each other. You're going to feel every rut and divot. But once you get it sliding across each other, they don't have quite as much time to hook into each other. That's really not quite what's going on at a quantum level, but it's a decent explanation that will suffice. So, example 3 says this. If I wanted to be completely accurate, I would say a 5 kilogram object sits on a surface with mu static, 0.3, and mu kinetic, 0.25. Cool, what does A want me to find? You know what's really wanting me to find? The applied force, because that's what we called this force coming from off the page. Is there also friction in this question? Is there more than one force? You know what this is a job for? What's this a job for? Free body diagram. There's the object. By the way, you may have noticed, without thinking about it, I usually assume we're trying to slide things to the right. There's no rule for that. That's just so our diagrams all look the same. So what are the forces acting on this object? Get the obvious one. Gravity. I agree. What else? I agree. Then we have this applied force. What else? Friction. Have we started accelerating yet, right, in part A, or are we just starting to accelerate in part A? I think we're, just at the starting point. So I think I'm going to say if I want to find the force required to get it to move, I need to overcome friction. Except here's the difference. Look up. Are we moving yet? Are we moving yet? I need to overcome static friction. Put a little S as a subscript to the FFR. Who's winning? Are we moving yet? It's a tie. So what does it's a tie mean as an equation? What equals what? Can you see it? Which way does this want to accelerate if I pull really hard? So everything to the right has to equal everything to the... That's if it's balanced. So what kind of an equation will that be? What's my force to the right? What's my force to the left? That's not a force. What's my force to the left? Friction. And if I want to be fussy, static friction. So we can say this. The applied force has to be bigger than, or in this case, it'll be exactly the same size as static friction. And if I pull any harder than that, it must move. Good yawn? With me? Have a little drink? Absolutely. And it wants me to find the applied force. Cool. Friction is what times what? I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. Yep. Now, are we moving yet? Look up. Mu static. That's how I know I'm going to use that one. We're not moving yet. What is mu static? They told me. 0.3. What's M? G? 9.8. How hard do we need to pull to even get this thing moving in the first place? Five times 9.8 is 49. It's going to be 49. What? Sorry? 14.7? Yes? Units? You okay with that, Christy? Thumbs up? Okay. B. Suppose I pull with 10 newtons. Christy, it says find the acceleration and find the force of friction. If I pull with 10 newtons, what would the acceleration be? You don't need to do any math. Pardon me? Why 0? How hard do I need to pull to even get it to move? Answer from A. How hard do I need to pull to even get it to move in the first place? How hard are we pulling in part B? So will it actually accelerate at all? No. So we can say this. A equals 0. How big is friction exactly? I'll give you a hint. It can't be 14.7. How big does friction need to be if I'm pulling with 10 newtons? Brian, 10 newtons to match me. You okay with that, Jacqueline? Jacqueline, how hard am I pulling in part C? Will this now accelerate? Okay. With me? I'm going to use the same free body diagram, except I'm just going to imagine this time that the applied line is longer because it's winning. Oh, who's winning? Who's losing? What does winner minus loser always equal? Now, here's the key. Look up. Are we moving? Yes? So, underneath friction, put a K. We're going to use kinetic friction. What's kinetic friction? Friction is still mu times the normal force, but since we're moving, which mu am I going to use? The mu K, which is smaller. This is why it's easier to keep something moving once you get it moving. Getting it moving is the bear. What are we trying to find? Well, first it says find the force of friction. So let's do that right over here. The force of friction is still mu times the normal force, but now it's going to be kinetic. I don't know the normal force. Oh, but look. I don't know the force is the same size as the normal force. friction is going to be mu kinetic mg. I've scrolled down. Was mu kinetic, was it 0.25? 0.25 times 5 times 9.8. How big is kinetic friction, the sliding friction? 5 times 9.8 is 49, so it's going to be, is it 12.25? No, yeah, 12.25? Yeah. Newtons. So there's the first thing. By the way, Cole, how hard did I have to pull to get it moving? How hard do I have to pull to keep it moving at a constant speed? That's why it's easier to keep something sliding once you get it sliding. Okay. And those of you that have moved heavy objects, oh yeah, this is what's going on there. What else does it want me to find? How to get the A by itself? Okay, so the acceleration is going to be the applied force minus kinetic friction divided by m. Jackie, I've scrolled down. How big was the applied force in part C? Sorry? 20? Minus, 12.25 divided by 5. What will this be accelerating at? What'd you get? Oh, you're getting your calculator out. You're going to practice these. Good for you! What'd you get? Negative? Can't be negative. 1.5 what? 1.5 even? 1.55? Meters per second squared. David, do you see why there kind of has to be two types of friction? Because that's what explains why it's hard to get something moving, but easier to keep it moving. There's two mu's. Having said that, if you go to the next page, I'm going to treat both mu's as the same thing. I did this question here where we used separate mu's, and I think there's a couple in the homework. I'm not going to ask you that on a test. You can just use I'll give you one coefficient of friction in the question. So, friction equals, Nick, what times what? Where mu is the coefficient of friction, and the normal force is from the, what does FBD stand for? Free body diagram. Okay. We just took a quick gander here. 1, 2, 3, and then one more after that. Oh, this lesson might be longer than I thought this was a shorter lesson. We'll see how far I get. Okay, so mu is the coefficient of friction. Technically static if you're not moving. Technically kinetic if you're moving. But I'm going to say, we'll just treat it like one thing. So I've done my fussy physics moment, but we'll ease up. Example 4 says this. Find the maximum force of friction between the mass and the following objects. This is technically mu static. Okay. What are the forces acting on this object? Get the obvious one. What else? And it wants us to find friction, the maximum force of friction. So, friction, Nick, is what times what? I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. What? And so I would say right now, it'll be 0.35 times 8 times 9.8. How hard would you have to pull to get this thing to start to accelerate? What's the maximum force of friction? 27.44. I'll keep the extra sig figs for a reason. So 27.44 newtons. Let's compare that with B. What's the difference between A and B? In B, there's an extra force pushing down. See it? Yeah. What are the forces acting on this? Get the obvious one. Gravity. Is this sinking into the ground like quicksand? Is it flying at you like Superman? So vertically, my forces must be, I'm looking for a word, the letter B, balanced. Why would I mark this wrong? Don't write that down. Why is that impossible? Sorry? Why is it not balanced? Isn't it canceling out gravity? It's also got to deal with that 55. So I'm going to draw my normal force a little exaggerated, like that. Tristan, this question is still saying find the maximum force of friction. So friction is what times what? No. You have never heard me say mu mg. Don't ever say that again. It is not mu mg. And I got to freak out here. Don't ever say that again. It is not mu mg. Friction is what times what? Mu times the normal force. And I don't know the normal force. Now, the reason you said that, Tristan, is here it's mu times the normal force. I don't know the normal force, but I noticed it has to be the same size as mg. Does this arrow look the same size as this arrow? Okay. I don't know the normal force. Oh, but look, okay. So here's our next strategy. When weird things are going on, Dylan, when you have extra vertical forces, are we sinking into the ground like quicksand? Are we flying like Superman? What that really means is everything down equals everything up. That's why you're not sinking or lifting off. Everything down equals everything over here. Let's put an equal sign. What's everything down in my free body diagram? mg plus 55. What's everything up in my free body diagram? Tristan, friction is what times what? Mu times the? I don't know the normal force. Oh, but look. I know some other stuff that's the same size as the normal force. What can I replace the Fn with? Not mg, but mg. That's the key. See it? Is that okay? So, how big is friction here? It's going to be mu bracket mg plus 55. Hey, what's mu? I don't know what's mu with you. What's mu? 0.35? M 8 times 9.8 plus 55. How hard would I need to pull to get this thing to start to move? .35 times bracket 8 times 9.8 plus 55. Whoop, that's wrong. 55. You get 46.7? No? Yes? Yeah. If I pull with 46.8 newtons, this thing will accelerate. In fact, really, if I pull with 46.700001, this will start to accelerate because that's the moment that my forces are not balanced. That's the maximum force of friction. Good blink? What about here? This is a job for a free body diagram. What are the forces acting on this M? Get the obvious one. mg, you all say? What else? Is this sinking into the ground like quicksand? Is it flying like Superman? Why would this be wrong to write? Pardon me? In fact, is the normal force here bigger, smaller, or the same size as mg? Well, someone said bigger, someone said smaller. The good news is one of them's right because it's not the same size. Has to be smaller. In fact, I can tell you by how much smaller. 55 newtons smaller than gravity because someone else is taking care of 55 newtons worth of gravity. Still wants me to find friction. Okay. Friction is mu times the normal force. I don't know the normal force. Oh, but look. I know some other forces that can help me figure out how big the normal force has to be. Emma, are we sinking into the ground like quicksand? Are we flying like Superman? So what I said now, a different way to think about it is that everything down has to equal everything. What is every force pointing down in my free body diagram? Just the one equals what's everything pointing up in my free body diagram? I'll give you a hint. There's two of them. Normal force and yes. Emma, what do I want to put right here? Just plain old Fn. Yes? Look here. How would I get the Fn by itself? How would I get the Fn by itself? How would I move the plus 55 over? Yeah, you do. How would I move the plus 55? How would I move the plus 55 over? What? What? So you're telling me, and you're right, that the normal force here is mg minus 55? And I can put that in brackets and walk it right over there. And this is why, Tristan, I reacted so strongly. It's never friction is mu mg. It's friction equals mu times the normal force, and you're going to have to figure out what it is. And it might be a boring question like A, where it is mg. I'm going to tell you right now, most of yours on the test, the normal force won't be mg. I'll stick an extra vertical force in there. I'll make it obvious. I'm going to try and trick you, but it's going to be there. Is that all right? Let's crunch the numbers, Emma. We get friction equals, what's mu? I don't know. What's mu with you? 0.35. And then it's going to be 8 times 9.8 minus 55. Oh, Pat, do you have a good calculator? I do. I can just backspace and change the plus sign to a minus sign. 8.19? No, yes, yes, no. Yes? So let's summarize here. If I want to get mass A accelerating to the right, I would need to pull with more than what? If I want to get mass B moving to the right, I would need to pull with more than 46.7 newtons. If I want to get mass C moving to the right, I would need to pull with more than 8.19 newtons. If I don't, then friction will match me. Do I have one here with a wonky normal force? Oh, there. Wow, I got a lot of ones here. Okay. How am I going to do this? We'll do example 5, and then I think we'll go to a video. But I'll get you started on the homework. We'll finish when I see it on Monday. Example 5 says, for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. You know what, folks? Let's do this. Let's divide our page in two. Oh, that worked well. Ha! If I use my scroll bar and just scroll down, it has a nice straight line. Oh, I went too far. Try that again, Mr. Duke. Cool. Small things. All right. look at the pictures. Is there more than one force involved here? I think this is a job for a free body diagram. Although, Brian, what I'm going to do instead, I'm going to label the actual picture. Instead of representing it with a dot, I'll label the stuff right on there. Before I go, let's do that right now. So, what are the forces acting in the first one on the 10 kilogram mass? Everybody get the obvious one. mg. Are we sinking into the ground like quicksand? Are we flying through like Superman? So, and I'm pretty sure the normal force must be the same size as mg because I don't see any other vertical forces. And if we're not sinking into the ground or flying through the air, everything up has to equal everything down. Okay? What else? See that 20? What name did we give last class to that force coming from off the page? It was the mystery force. We didn't care what was causing it. Yeah, F applied. Am I supposed to include friction in this question? Yeah? How do I know? Hey, what's mu? I don't know. What's mu with you? Yeah, they gave me a mu. Which way will friction be pointing? That way. And I'm going to gamble. I suspect it's shorter. I think the 20 is winning. So I'll write that in there. So the free body diagram on the right-hand side. What are the forces acting on the right-hand one? Get the obvious one. What else? That 15. I noticed it. Which way is it pointing? Down. What else? There has to be a normal force because we're on a surface. Will the normal force be bigger, smaller, or the same size as mg here? Because it's got everything down has to equal everything up. The normal force here is having to cancel out that 15. This would be a nice question as a test question to ask you to draw the free body diagram for. And I would take marks off if you made normal force the same size as mg or shorter than mg. What else? Well, we still have this 20 from off the page. Here's the F applied. What else? What else? Yeah, friction. Which way? Okay. We're going to do these simultaneously. So I'm going to put a letter A there, put a letter A there. Maggie, what does A want me to do in the first one? Well, in both of them, right? The one on the left, are we sinking to the ground like quicksand? Are we flying like Superman? So everything down equals everything? Can you write me an equation that says that? Everything down equals everything up? What about this one, Maggie? Everything down equals everything up? Everything down, mg. What else is down? Yes? Equals everything up. What else is up? Yeah. So just go systematically. Don't try and jump around. Cool. Cool. Chloe, what does B want me to do? Tristan, friction is what times what? Times the normal force. I don't know the normal force, Chloe, but I'll write that down here. And you know what? I'll write that here. Look. I remember the force is the same size as the normal force. Here, what can I replace the normal force with? Good. So I'm going to go like this. Mu mg. How big is friction? Mu 0.12 times 10 times 9.8. Oh, I think I can do this in my head. Sure I can. 10 times 9.8 is 98. 9.8 plus 1.76, 10.8, 11.56? Double check me. 11.76. I carried it. I thought I had that to 4 sig figs. I was proud for a second there. 11.76 units, Chloe. Newtons. B. What did you say, Tristan? Friction is what times what? I don't know the normal force. Oh, but look. I know what I can stick in for the normal force, Chloe. What can I replace the normal force with? So it's going to be mu bracket mg plus 15, which is going to be, hey, what's mu? I don't know what's mu with you. 0.12 mg plus 15. Plus 115, Mr. Duke? Plus 15. I think I can do this in my head. 10 times 9.8 is 98, plus 15 is going to be 113. 0.12 times 113 is going to be 11.3. No, yeah, plus, double that, Mr. Duick, 2.26. So it's going to be 13.3, 13.56. I got the decimal right this time, right, Emily? Is it 13.56? Thought I was getting old for a second there. You are. Shut up. Okay. Sierra, what does C want me to do? Look at the first picture. Who's winning? Horizontally. Who's winning? Who's losing? What does winner minus loser always equal? There. Look at the second picture. Who's winning? Yeah. Who's losing? What does it equal? You mean I get identical equations horizontal? Yeah. I do. What's changing is the friction force, and that's going to give me different answers, but it's the same physics. It's the tug of war between the applied and friction. Every time I look over. I've scrolled down. Hannah, what does D want me to find? Oh. See the equations that Sierra gave us? How would I get the A by itself? So I get A equals F applied minus friction divided by M. A equals, and I love the fact that for different situations, we're still getting the same equation. What's going to change is the parameters of the variables we put in here. Let's keep going, Hannah. How big is F applied? 20 minus 11.76 divided by 10. I can do this in my head. It's going to be 20 take away 11 is 9, take away 0.7 is 8.3, take away 8.24. 0.824? Double check me. Am I right? To 3 sig figs? Hannah, units. Here, it's going to be 20 minus, what was it? 13.56 divided by 10. I can do this in my head too. 20 take away 13 is 7. Take away 0.56 is going to be 0.644? Yeah? I'm dividing by 10. I should be able to divide anything by 10. If I can't, I'm in trouble. We've been talking about mu. Here is some different coefficients of friction. So, just to give you an idea of numbers that are really big and really small. Steel on ice skates near 0. Ice is slippery. Steel on ice is even slipperier. That's why with skates you can glide for so long. Rubber on ice is even worse. Rubber on wet asphalt, rubber on dry asphalt. Actually, depending on your tires, you can get this up to about 0.75. Also, on hot days, your traction increases because the pavement itself gets stickier on the really, really hot summer days. So this one varies. By the way, you don't need to memorize all of these. This is purely to give you an idea of when you're solving kind of what you might be finding. This is me being a nerd here. Steel on steel, if we grease it down. Sorry, well, steel on steel, if we don't grease it down, 0.5. So we add oil. Otherwise, that's a lot of heat you'd be generating. Can we have a coefficient of friction bigger than 1? Yep. Rubber on glass has a mu of about 2, approximately. I told you earlier in class, dragster tires have coefficients of friction bigger than 1. Oh, yeah, there we go. We'll continue with that next class. Questions, don't hand this in, but if you want to get a head start on the homework, I'm going to add more. But questions that you should now be able to handle. Number 1, 2, 3, 4, 5, 6, 7. I'll finish the lesson off. I'll be giving you some more next class, but I got a video to show you.